Guten Tag, hallo. Jawohl, schön. Nach der Flut kommt jetzt ein schöner Vortrag von Sven Martin Hallberg und der geht darum, in Englisch auch. We're gonna have a talk by Sven Martin Hallberg and it's about how the Swedes hacked the Nazis and have fun. A warm welcome, please.
Yeah, hello, okay. Yes, the talk is titled Swedish Analysis of Nazi Crypto TTYs. Crypto TTYs, means teleprinters with automatic encryption. In particular this device, it's called Siemens & Halske T52. Which is less well known than the famous Enigma, but had much stronger crypto. So, it's an electromechanical teleprinter. That means, well, you take two of these, hook them together by wires, type the keys, and it does the crypto on the wire, right? That means it's automatic. And well, one reason why these things are less well known is they were really heavy, 100 kilograms or something. That's why there were not many of them in operation and only on high levels and for very important like diplomatic traffic or stuff like that. Okay, here just for comparison, the Enigma, which was a pretty simple device in comparison. It consisted only of a few, the switches, a few plugs, and lamps with the which the ciphertext would appear on, and you would have to write everything manually. You know, you'd have your message, and then you would type the key, and you would write down the ciphertext yourself. This made it a very comparatively lightweight thing that was used in the field, and many of them were manufactured. So that sets it apart from this, from the T52. Also, well, cryptographically, the Enigma, some of you may know it, was a relatively simple substitution cipher by today's standards. The T52, in contrast, used something, well, it used a stream cipher as we know it today, an XOR actually, and something additional which I will get into. But so you can really compare this to, say, WEP encryption, and you can also compare the way it's cracked to WEP. So that makes it a little interesting. Okay, so for the overview of the talk, at first I'm going to explain something about the political and technical setting of the time. This is 1940s, World War II is in full swing. And well, this is going to be pretty short, only what you need to know. And then we're gonna go into how it was actually broken by the Swedish team, which includes obviously, well, deciphering some messages, then finding out what the algorithm actually is that's used by the machine, and then actually finding out the real buildup of the machine, including all the wheels and patterns and whatever it means. So the Swedes would have actually been able to build a T52 on their own. And in fact, they did something quite similar. They built things to decrypt automatically. And then I will conclude. So let's start with the setting. It's 1940. That's when this whole thing started. A situation is as follows. Germany is at this point still neutral with Russia. They had this pact. And Russia had just invaded Finland, and Germany was busy fighting the Allies in Norway, because Norway was important for the iron or something, and well, so Sweden was technically neutral but surrounded by fights. So they were eager to know what was going on, and that's why they formed a cryptanalysis division of their military, which was actually founded pretty early already. when they started breaking the T52, they had it already well set up, which was due to, well, good foresight by one of the main guys, which I'm not going to go into that much because he wasn't directly involved with the T52. But that's important, so they had already gathered lots of experience cracking other traffic from all over the place, Russian, French, English, and so on. So they were routinely intercepting radio traffic at the time already. And what they were usually breaking were codebook ciphers. That is, you have a big book that lists for every major word a certain code number, and then you would just, substitute and maybe do something else. For example, the Russians, they super enciphered, they substitute all the words, and then they would encipher the resulting text with a one-time pad. And here the key figure appears, which is a guy named Arne Bäuerling. He was head of the Russian section, decoding their super enciphered code books, and in the end, he ended up with the T52s. So first, for his background to the Russian code books, as I said, per word substitution. And then they super enciphered with one-time pads, but because the one-time pads have the problem of logistics, they just reused parts of the pads. So every message, they would just pick out one part of the pad and use that and do this over and over again. So that leads to when you encipher the same message with the same one-time pad, you end up having the same ciphertext in places where you have the same plain text already, right? This is called a repeat, and that's what you use in breaking it. So that's his background, and it should prove useful for the T52. So at some point in 1950, he gets a ton of unusual looking intercepts on his desk without at first knowing what they were, where they came from. He just found them on his desk and looked at them. One thing that stood out was that the symbols weren't grouped. Usually when you do hand crypto, you group the characters in groups of 5 or something, so it's easier for a human to process it. And these were just really long strings. And they used 32 characters, the 26 letters and 6 digits, which everyone notices it's a power of 2. So he concluded this is probably machine crypto, which was a rare thing at the time. Okay. Well, severely unreadable, that's a quote, by the way, from one of the interception guys. The Germans were initially sending the traffic in the clear, and then the machines would switch over at some point. And the guy said, well, look, our intercepts suddenly became severely unreadable. Funny way to say it. Well, by the way, they were, what I forgot to say, they were intercepting these from their own lines. The Germans had leased telegraph lines going through Sweden in order to communicate with their troops in Norway. That's how they were getting these intercepts. So they put up a listening station on their own lines and just intercepted everything. Okay, so now I'm going to go into a little bit of the technical background of that time. The teleprinters used a standardized alphabet known as Bordeaux code, or ITA2, which stands for International Teleprinter Alphabet number 2. It uses a representation of 5 bits per character, and that explains the 32 characters he was seeing in the intercepts. I'll show you a diagram in a minute. And because 5 bits aren't that much, they were using 2 modes. They were using 2 modes for the machines, letter and figure shift. As the name implies, letter was for letters and figures had special characters in that mode. And there was a control code that would be sent and switch the machine into the one of the two modes. Here you can see that this is a table, an abbreviated table of the teleprinter alphabet ITA2. It starts with the letters, and then you have the 5-bit representation. These were sent over 5 wires in parallel, if I recall correctly. And here at the lower part, you see the special characters, character to a new line, and here's letter shift and figure shift. These are the important ones. And well, here, this is the notation that they used in the intercepts, because so they used the digits for the special characters in order to make them visible, because in the ciphertext you couldn't tell anymore anyway. And this doesn't include the digits, so it's not ambiguous. You see. So that's why you see this strange representation where you have the normal characters and only 6 digits. So the digits in the following are always representations of the special codes. Okay, well, teleprinter cryptography in itself was not entirely new. It was in principle known, the technique to, well, bitwise XOR the plain text with a key stream, and it was also a known idea to use a pseudo-random number generator for the key stream, and the random numbers were usually generated. This was also a known technique by pinwheels. I'll get into the details of what that is exactly in a second. So you would have a bunch of wheels in the machine, and they would turn and spit out random bits. In particular, the wheels were circumscribed with random bits, basically. The bits represented by little pins. That's why it's called a pinwheel. So you would have the little wheel, and the little pins on it, and they would be read mechanically by some kind of feeler thing in the machine, and then you would turn the wheels in order to generate a new bit. If you wanted to have multiple bits, like I said, the machines they use 5 parallel lines for the characters. If you would want to have 5 bits at the same time, you would use 5 wheels. And well, the wheels have different numbers of bits on the circumference usually, and in fact they usually have co-prime numbers because that maximizes the period of the whole thing. If you have 5 wheels and you turn them 1 step for each character, then, well, at some point you will repeat the sequence of random bits, right? And well, you maximize that if all the periods of the individual wheels have no common factors. So you can. So what you use is the least common multiple of the whole of all the individual periods, and then you get a maximum period for the entire random stream. So this was the basic technique, which was already known, teleprinter crypto. So let's see what they did with the intercepts. Yeah, first this little disclaimer. This was, well, the original T52, there were several models. Later models were a little bit harder because they improved the way the wheels worked. I just said the wheels all step in in sync with every character. They changed that later, and it makes it a lot harder because they don't repeat as predictably. Well, the original one, though, did step in sync, and it was broken in just 2 weeks by him, without him actually knowing much about this whole stuff at the time. But it's safe to assume that he kind of familiarized himself, of course, after having noticed that it's machine crypto. But Boiling himself refused to talk about much of how exactly he did the analysis, remarking stuff like, well, a magician doesn't reveal his tricks and stuff like this. So this whole talk presents a plausible reconstruction only. It's based, I might add, on 2 books about this topic. I will tell you which ones in the end, where everything is explained in much more detail. Okay. So you should keep that in mind, that this is not certain. When I write in the following, well, from this it is clear, and you see here, and blah, 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 it means, well, we think that probably this is what he did. Okay. So let's look at an example of one of these intercepts, what they would look like. You see here, this is the ciphertext, or actually it starts with plain text here, it's German for here, and stuff like this, blah, 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 blah. And you see these digits in the middle, in between the words. These are not ciphertext, these are just abbreviations. I will explain them in a second. The digits, remember, they mean the special characters. So if you see 3, 5 in the intercept, it means it's a letter shift followed by space. It's actually just meant to be a space, but the operators had the habit. This is going to be important in a moment. The operators had the habit of pressing 3 and 5 consecutively to get a space, because, well, it would ensure that the machine was in letter shift for the next word. Because sometimes the line noise would cause the machine to erroneously switch into figure shift, and you wouldn't be able to read anything. And this habit kind of suppressed that. You would be sure that you're again in letter shift for every new word. Okay, so you see here. This is written out without the special characters. So you see here MBZ QRV, and then we have a 5-4 here that makes the I think, does that make the 5-4B? 5 is a space. I forgot that down here, but okay. And 4 figure shift, and B is probably the code for the question mark. And then it goes on, 3-5 space KK, 3-5 QEP, blah blah. And then figure shift again, and lots of stuff. These are these numbers. And then you get to the end, blah blah blah. Here 3-3-5-5, lots of spaces. And then you get and VV. And these are the codes that switch the machine into crypto mode. And after this, everything becomes garbled. This is actually the ciphertext. You see one more space, and then ciphertext. Let me explain the abbreviations shortly. Here I said it means here. MBZ is the name of the sending station, and QRV was a standard abbreviation among, well, teleprinter operators and maybe also in radio operators, which means just do you read, like do you understand? This will be important in a moment also, because this is a word that was used very often for obvious reasons. And KK is just for German klar, clear, everything's okay. So, oh yeah, also notice that this is intermingled. These are the 2 stations talking in alternation. So you see, this is here MBZ QRV, do you read? And then the other station responds okay. And then you get this QEP, blah, blah, blah numbers. This is, I can tell you, this is an initial vector, basically. It's the part of the crypto variable that changes. So this is what one of the stations says, okay, let's switch into crypto mode with these initial parameters. And then it says which means umschalten, switch over. And VW means verstanden, understood. And this exchange, one station says the other says VW, and this would automatically switch the machines, or maybe semi-automatically, I don't know, but it's not important. And then they would talk in the secret. Yeah, okay, so you can see what is likely to be used for an attack. Well, I said the QEP numbers represent an initial vector for the crypto. you have one part of the well, crypto variable of the key, which is secret among the stations. It's probably distributed over other channels and changed once a day or once a week or so. And then you have the IVs, these QEP numbers that would be added in order to avoid sending the same message with the same key, or a different message with the same key, I mean, right? Because that's the problem with the stream ciphers. You can't, you don't want to send different messages with the same keys. So, okay, so what would happen is that the operators would reuse the same QEP numbers, and then you could just exploit that, which you will see how in a second. So, and then we've already seen the frequent use of typical sequences, the 3-5, obviously, and also QRV is very common. And this will be important because you can assume that it will also be common in the ciphertext. Okay, so now let us suppose that we've actually received a bunch of intercepts that were a bunch of crypto messages that were indeed encrypted with the same key, so on the same day with the same QEP numbers. As a side note, this was actually not so uncommon because the machines in the beginning had a technical, like a mechanical or design flaw. The machine had an actual reset button that would reset it to a certain preset state. And the operators would often do this just out of because it's convenient. For example, if your line noise garbled your state, the machines get desynchronized, and everything has to be reset somehow. And then they would just push this button, the machines would be reset to the original state, and they would go on. And then you would have a different message, maybe a little bit different, maybe a little bit more, but with the same key. So you could expect to get lots of these actually messages, as it's called, in depth. When you get more than one message with the same key, then it's called a depth, or at least in the jargon of the time. So let's assume we've got these, and a number of others. I only show 4 here. This is not enough for the whole analysis, but it won't fit. So you'll just have to accept them as a little, yeah. I have a paper version of the talk where you can see the whole example with, I think, 10 messages, and you can look up the details there. Okay, so we've got these messages which we know nothing about, and they are again, but we can look for stuff that appears a lot of times. Especially B graphs. That is 2 characters after another. So, for example, we have here, it appears a lot of times. This is one thing you can't see in this because it's only 4 messages, but if you look at the 10 messages in the paper version, you would see appearing a lot of times. You would see ZGJ1 appearing a lot of times. You see here already ZGJ1 is here, and it's again here. And here's and WF is also one that would appear lots of times. This is something you'll just have to believe me now. And well, what you can do is you can just guess that, well, these repeating B graphs are probably 3-5s in the plain text, because, well, to repeat a B graph, that's to have a B graph at the same position in 2 different plain texts is not so common. And so in order to get the same ciphertext also at the same position, you would have it gets much more unlikely. So if you do see that the same ciphertext appearing over and over, it's very likely that it must be a B graph that is very common, that appears very often. So that's why you can assume here these are probably 3-5s. You also see these are 3-5, 3-5, one after another. This is something that was done in the example here. You see 3-3-5-5 or something like that. It could happen. The operators would just repeat stuff in order to make sure that it went over correctly. Okay, so we've got these little assumptions here about plain text, and now we can look further. And well, what we can do is we can guess that it's a substitution. No, it's an XOR cipher, because this is what, well, I said was common or already known at the time, and so this would be our first guess. Well, this implies the characteristic weakness of XOR ciphers, which is that, well, if you the plus here is an XOR, okay? This is addition modulo 2. So and if M and M prime are the two ciphertexts, you XOR them. Well, the keys cancel out here, right? You've got this is the first message with the XORed with the key stream. This is the second message XORed with the key stream, and well, it has an associative law, and it has and it commutes. So you can pull the key over here, and it cancels out. So you get just A plus B is the same as M plus M prime. Okay, this is just a characteristic when using this kind of cipher, and well, you can just check if it holds to check your assumption, your guess. And in fact, in our case, it doesn't. So the machine is not exactly using an XOR cipher, but it almost does. If you do it, you take, for example, the 3 and the 5, and the U and the G, encrypted with the same key. That means encrypted with the same key means they appear at the same position in the messages. If I go back a little, you can see here, if you look at one column, you know, at this point, if these messages were encrypted with the same key, so at each column the machines are in the exact same state, unless they take input from the plain text as permuting the state. But this is another. This I think was not common at that time, and well, you can just guess it, and then you will find out that it all works out. So let's assume that after in each column the machines were in the same state. So you can look if you find a U and a G and a 3. No, if you find in the plain text 3 and 5, and in the or like here, and you see in the ciphertext a U and a G in the same column, you know, because of this characteristic, that if you add the U and the G, the ciphertexts, and you add the 3 and the 5, the plain texts, then you should get the same thing, right? Okay, so that's what we're checking here. We take the U and the G and get this, and we take the 3 and the 5 and get this, which is almost the same, just that it's permuted somehow. It looks pretty much the same, just the 0 has moved around, and maybe the 1s have also moved around, which we can't see, but we can see that the 0 has moved. So, and if you do this for other examples, and then you will find that they all show the same effect. You can look for other characters that also, you know, add to something which has only a single 0 or a single 1. Then you will see the exact same effect on all of them. So you can guess further that, well, maybe it's not an XOR, but maybe it's an XOR followed by a permutation. So this is the hypothesis that Boiling made, that you get the ciphertext message by, well, first super enciphering with a pseudo-random key stream, and then applying a certain random permutation sigma. Okay, let's check our hypotheses, or actually, well, just as a side note, at this point, it's not entirely clear whether the permutation is done before or after the super encipherment, right? It could also be that you first permute the plain text and then XOR, or it could be the other way around. But I'm going to tell you right now that the machines did the XOR first and then the permutation. You can check that for certain things in the analysis it doesn't make a difference, and for other things, well, you can check it later. Like you can work with it, and then you will get a little bit. You get a certain error in the key stream you would deduce, and then you would check it against something else in the end and find out, oh, this doesn't work out, and you would go back and try the other way and then find out that this works. I'm going to save you that and tell you right now that it's not this case, it's this case here. First XOR, then permutation. But we got the idea for the permutation from, well, the moving around of these characteristic bits here. Okay. Now, well, we know we've got an XOR and we've got a permutation. One question, which is slightly technical, is no, actually, okay. Now let's first try. I'm sorry. Let's first try to actually find out which permutation was used in a certain column of your intercepts. And you can do that by, well, finding these characteristic pairs of characters which have only one single 0 or a single 1 in their difference. Because then you can look at the difference between the ciphertext and the assumed plain text and see where the characteristic bit has moved. So you would know, for example, in this before here, oops. Here you can see, well, this is your assumed plain text, this is your assumed ciphertext. So you see that the 0 here, you know that, like I said, they should be the same if it was just the superposition. These should exactly be the same. So you can see the permutation moves a bit from position 3 to position 2. So you can see, well, one part of the permutation is moving bit 3 to position 2. And if you do this for different pairs of characters which have the characteristic bit in another position, then you can deduce the entire permutation, because the permutation can be broken up into individual. You can just see, well, this one moves here, this one moves there, and so on, and you'll know the permutation, right? And what you need is only 4 of these characteristic bits, because it's 5 parts, and if you know where 4 of them move, well, there's only one possibility left for the last one. So you only have to find 4 of these pairs, and, well, we're lucky. I told you before that the QRV was also a very common thing in the texts, and actually combining 3, 5, and QRV gives us 4 pairs that will do the trick. You see 3, 5, I already showed you, has the characteristic bit in position 3, then 3Q gives the 4, QR gives 2, and 3V gives 1. And then the 5th bit is obvious where it moves. So you can deduce the entire permutation by finding these 4 pairs in one row of your intercepts, right? That is, you have a few messages encrypted, or a few plain text characters encrypted with the same key. You know that because they're in the same position in the intercepts, and you just look at where you take the ciphertext corresponding to these plain text characters, XOR it, and see where the characteristic bit ended up. Okay. Well, maybe I should go back to the picture. It might make it a little easier to understand. Right, so here you see GU35 in this row. That is, you know, this has the same ciphertext, the same key, and well, you look at the 3, 5, you know they have their characteristic bit in position 3, I think, and you look at where is it in GU, right? You XOR GU, and then you see, okay, it's in position 2. So you have one part of this permutation for this column, and then you can do that. Then if you find in this column more of these pairs of characters that I just showed, then you can find the rest of the permutation for just this column. And then you have to do this over for the next column and so on. This is a tedious process, obviously. You'll have to make some guesses here and there, and but in the end you will find enough of these things. If you have like I don't know, like 20 messages or 30 messages, they would, I think, receive up to 100 messages with the same key on a day. So they would have enough of this stuff, and you only need to do it once, because afterwards I'll show you that you can figure out the entire machine state and then do it all automatically from there on. So so you have to do a little guesswork in the beginning in order to guess enough of these things. Note also that once you find the key for one of the columns, right, it's completely clear what the rest of the plaintexts are. You can just once you because these are have the same keys, the same key, well, words or characters, and then you can. It's like filling out a crossword puzzle, right? You know the key from somewhere here, and then you can fill in the rest of the column, and then you can probably guess more words, and then the words stretch over to in this direction, and you have more columns which you can work with, and maybe you'll figure stuff out there. Okay. So. Right. So let's assume we've uncovered a lot of these permutations, and the question becomes, well, how are the key stream bits actually generated, or how is the permutation generated? Well, the key stream bits are probably obvious. It's safe to assume that they are done with pinwheels because this was the known technology of the time, and well, we can assume that Arne Beuerling did this. He assumed that they were using pinwheels for the 5 key stream bits for each character, and the question is now, what do you do for the permutation? Because this was something new. And then we know that he said he remembered seeing relay switches used in telephone exchanges. You would have a relay switch which would, depending on the input, choose one, well, send, well, depending on an input bit, it would either cross, no, it would send the current in a wire either one way or another way. And if you combine 2 of these switches in the right way, you can build cross switches that would have an input of 1 bit and take 2 wires, and depending on the bit, they would either cross the wires or just pass them through. So you could have basically, and these would, so if you take your 5 signal lines in the teleprinter, and you want to permute them somehow, the signals, you can put cross switches in between these the individual wires at some positions, and well, transpose the bits that way. So this gives you, in theory, any permutation you want, because you can decompose every permutation into a series of transpositions. And then you could use pinwheels again to generate the inputs for these cross switches. So so this is the next assumption that would be made. Well, okay, they're probably using this kind of switch, and then they're probably, or almost certainly, they're using pinwheels to generate the inputs for them, and thus they get this random permutation. The question then just remains: how many switches do we have in the machine, and in what arrangement on the wires? Because we see the permutation, we see the result of the switches, but we don't see the input bits for the switches. And this is what we want to know, because we want to know the actual machine state. So, and also it's likely, or it would appear likely, that they wouldn't put a full set of cross switches on the wires, like because these were not exactly small. They were actual relays, and 2 of them probably for each switch, and so on. So it might be, well, it might not be a ton of them, but only some wires possible to be transposed. So, but well, we can find this out pretty easily by just looking at the permutations that actually do appear, because we know we can decompose them into transpositions. Well, let's assume, well, we have 5 wires. Okay, so we have these permutations with 5 elements, and let's say we've discovered a ton of them by this manual method mentioned earlier, and then you just decompose these transpositions. You can uniquely decompose them into these cycles, and then you can split them up. So you would know, okay, we have this this permutation here. This notation is supposed to mean bit 1 is sent to position 5, bit 2 is sent to position 3, bit 3 to position 4, and so on. And this is supposed to be the transposition which exchanges bit 1 and 5. This is supposed to be a cycle that puts 2 to 3, 3 to 4, and 4 to 2. And so these are, and then it's split up in this way. Not exactly important, the mathematics, but the important part is that you can decompose the permutation here into 3 transpositions. And that way you can deduce that, well, the machine will have to be able to switch wires, to cross wires 5 and 1, 2 and 3, and 3 and 4 in order to implement this permutation. And if you do this a couple of times, you will find out that, well, there are never more than 5 transpositions involved in the whole thing. And so you can assume there are only 5 switches, and you would know because you see which ones you need, and then you could make a very good guess at that a certain pattern of cross switches was used. For example, like this. This matches with our example. These are supposed to be the 5 wires. These are supposed to be the 5 signal wires, and each X represents one of these cross switches. Well, so this is the 1, 5, and this is the 3, 4, this is the 2, 3, and then an additional 4, 5, and 1, 2. So these 5 switches, this would be a typical setup, and you could discover this just by looking at the permutations that actually appear. So now, well, we know pretty much what the machine is built like. We know it's a we know we have these pinwheels, and we have these permutation switches, and then it's basically just well, it does the XOR and the permutation, obviously. Now, well, it has 10 pinwheels. That's what we know now, because we know we have, or we're pretty sure that we need 5 keystream bits for each character, and we need 5 bits for the permutation for each character, and it's safe to assume that the machine processes 1 character each cycle, because that's the way these things worked. Okay. So we'll assume that the T52 has a drum of 10 pinwheels inside that generate 5 bits for the keystream and 5 bits for the permutation. Now, the only thing that's missing for us to be able to, well, say, build our own T52 would be to know the patterns on the pinwheels. I said that, well, the pinwheel is inscribed or circumscribed with a pattern of random bits. So we would have to know these actual patterns, but they're easy to find. If you decipher a long sequence of text, like the one I showed in the example, you will find the permutations, and because we've deduced the switch arrangement, we know which bits the wheels will have generated in order to produce this permutation. And well, we also know the key. If we deciphered everything, well, you know, then we can calculate the key. I left out the actual calculations in this talk for brevity and not to bore you with too much mathematical formulas and stuff. But you can read that in the paper version. It's not hard or anything. I just didn't want to put so many formulas on the slides. So well. So you will get, if you do this, if you decipher a long sequence of text, you will get a series of 10-bit words, and well, you can just look at them. You can just see when do they start repeating, and which is the bit pattern that appears in a certain place of the 10 bits. You know, each bit is generated by one wheel, and so you will see which are the bits that are generated and when do they start repeating. And that is, at that moment, then we know the complete machine state. And just as a note, indeed, if you would do this, you would find that the wheel patterns that you derive in this way, not the patterns, but the periods, I mean, the number of bits on the individual wheels are indeed co-prime, which maximizes the total period, as I mentioned earlier, and so supports our assumptions. Because otherwise it wouldn't. It would be unlikely that the numbers would actually appear so conveniently co-prime. Okay. So at this point, we're actually done with the machine. We've derived. Well, we knew it was a 5-bit Bodo code teleprinter. We've established that it's an XOR cipher followed by a random permutation, and we know the bits are provided by pinwheels, 10 pieces of them, and we know the patterns on the wheels, and well, at this point it's also easy to figure out that the QEP numbers seen earlier, they provide initial positions for 5 of the 10 wheels. It was 5 numbers. If you don't recall, 5 numbers given before the message, and they would set the initial positions for 5 of the wheels. This is pretty obvious, and the rest of the state, that is, which wheels were controlled by the QEP numbers and what their initial positions were, these are part of the secret state that was changed through a different channel, like once a day or once a week or something like that. So that would be the static crypto variable, and the secret part, and the QEP numbers are kind of the varying part of the crypto variable for each message. So at this point, you know exactly what to do if you get one of these messages. You just initialize the 5 wheels with the given numbers, and then you can mechanically decrypt the whole message, just as the real machine would, once you've discovered the rest of the state once, for the until they change it. But they would, you know, it changes once a day usually, or something like this. So that's so that allows us to do what the Swedes did. They promptly built automatic decryptors, like, you know, put a machine together that, and you take your team, and with every day they would start getting these intercepts, and once they have enough of them with the same key, they would start this manual process, which is a little tedious but would get done in a few hours, and then you deduce the permutations and the patterns on the wheels, and these actually didn't change, it turned out, but still you have to check. And then you know everything, you initialize your own machine with it, and then you just have to, for each message, type in the QEP numbers and type in the ciphertext, and it would spit out the clear text. And this is exactly what they did quite successfully for a time. Yeah. So this wraps it up, really. So just to conclude this talk, what I wanted to show was that, well, cryptanalysis is not necessarily only black magic, but well, you can have success by just taking a bunch of experience, which is, you know, they decrypt these code books and just tried in the beginning, just tried doing the same thing that they did with the code books. That is, looking for repeated sequences of characters in the intercepts, and they actually had success with it. So you take this experience and you take some intuition, of course, which is like, you know, making the right assumptions at the right places. Well, if you lack intuition, you'll just have to be a little more, a little bit more, you'll just have to need a little more perseverance. And this is the other important thing, which is, you know, you don't give up. They just, these strange looking intercepts come in, and you just try something what you already knew without knowing anything about them, and you find that it works, and then you reason. You do a clear assumption, and then you follow through, like making deductions from that, and you say, well, if we assume this, then it would have to show the characteristic of a stream cipher, and then you check, oh no, it isn't one, but it looks a little bit different. Then you make another assumption. This is just clear reasoning, and well, being perseverant in the sense that when you're hit with something like, oh, it isn't a stream cipher, you don't give up, but you say, well, what can we learn from that? And then you get your success in the end. So this is, I think, a little bit interesting, and like I mentioned, this is, well, it's being a stream cipher, it's kind of comparable to wireless WEP things, so yeah. I hope this was kind of interesting thing. And for the at the end, let me just give you the references to the two books. This is based on, this was actually written by me for a university course. Based on these books, one is called Code Breakers, and the other one is called The Geheimschreiber Secret. Geheimschreiber, that's what they usually call these machines. T52 is the official name. Geheimschreiber in English is secretly writer thing. So this is by Frode Weyrot, which is also the guy who wrote a simulator for these machines, actually. I just found this yesterday, which you can download and run and see the machine in action. I've also put this link on the Fahrplan page, so you can just look it up there. Where you can also get the slides and the paper version of the talk. Yeah, so this is these are the two books. They give a lot more detail. They give historical accounts, and they also go into detail about the later versions of the machine, which were harder to break. You see here T52D. This is version D of the machine, which is already a little more advanced. That's what the books also talk about. Yeah. So yeah, thanks for listening. And do you have any questions? No questions? Okay. Thank you.